See here, I need to set up a couple things still. Looks like we got sound of the OBS. It's fine. Okay. Almost there. Okay. So good morning. Hello, everybody. My name is Foamy Guy. If you're new, my name is Tim, I should say. I go by Foamy Guy on GitHub and Discord. We're working on CircuitPython stuff. If you're brand new to this, if you're catching it in the future, don't know what I'm talking about, CircuitPython.org is a good place to learn more. It's basically a version of Python that runs on tiny computers, like this little one here. The actual computer in this case is inside this chip on the back. We're writing Python code that runs on this little device. In this case, it also has a display on it, and the Python code that I'll be writing is to deal with the display. How's it going, C. Grover? Good morning. CircuitPython.org, though, you can learn more. Also encourage you to join us over on the Discord if you want to get involved or learn more or get help with CircuitPython or your project or your device or anything like that. Is that one linked below here? This one? Yeah, it's on the bottom down there, adafru.it/discord. That's also the Discord that's below me there. We're in the live broadcast chat, so if you happen to catch this live and want to ask a question about something I'm doing or something related or unrelated or whatever, that's the place to do it. And I'll say thank you to Adafruit. This is their website. I don't know why it took me to a login page. Can I just go to the page? Interesting. I cannot just go to the page. Interesting. It's gonna two-factor after that even. All right, 1 second, I guess. We'll log in real quick. I could go to a private browser, I guess. I don't know why. Maybe it's because I did remember me. It's like, gives me no choice now. It must remember me. That's probably what happened. All right. This is their website, the front page of their website, which you do not have to log into normally if you don't click whatever I did at some point in time. They are a hardware and software company based out of New York, and they are the ones paying the folks that work on the CircuitPython project. They pay some members of the team to work on the project full-time. They pay some members like me to work on the project part-time. to do stuff, around the periphery, right? Some of us are getting paid to write Python code, but also projects, documentation, support, all kinds of different things go into CircuitPython, fostering the community, putting together, blog posts and things for the community, videos, all these different kinds of things. Adafruit pays folks for, the folks that are working on CircuitPython in particular, as well as other folks who don't necessarily work directly on CircuitPython. So huge thanks to them. And of course, huge thanks to anybody who wants to purchase hardware from them, because if you purchase hardware from them, that is helping them continue to pay all of us to work on all of these interesting things. So thank you to all of those folks. Jumping straight in where I want to get to, you got the gradient tool. Let me check out this one. Okay, maybe this one is what we want. I may try to implement this. I'm interested to see if I can take the code from here and make it work with CircuitPython, even if as an exercise. I will check out yours too, though, and see what this does and see if it works the same as this or different, or how this works. Nice. Normalized index. Oh, interesting. Okay. How do we do? Okay, so we just go spectrum tools, index. So this one will give you. Oh, interesting. So this is kind of like wheel. Is it kind of like the way wheel, like Rainbow IO? You give it a number, or in this case, you're giving it two numbers, and it's giving you back a color, and you essentially can iterate through numbers or whatever, right? You can iterate through, and it will continue to give you colors that are next to each other. Is that how this is going? Or this is just index, although they do all give you the same. Interesting. It's because of the different bits, which is what this is explaining, I guess. Output will be limited. Visible. Right. Okay, so these are the differences. I was like, these are the same code, but differences, but the import here. So there are different methodologies for deciding which color is going to come out based on the number you give it. What is the number? What is the 1.0 there? Gamma. No, gamma is the first one. Show up here too. Okay, this I think is closer though. So this one is like you give it the three colors, you ask it back for the index. So this I think is the most similar thing that this page implements. Let's try this one. Is this one and my device is not on actually. Let me see. We probably need to push this. There we go. They have base. Let's go there. Good morning, DJ Devin. InColor uses a list for a custom spectrum gradient. Is this the root group test? I think this is the same. Let's compare. Compare with Control D. I'll try to remember that. Probably won't. Control D. That's dangerous because it's like close out of terminals and stuff. Okay. They are the same though. So we can just take CodePy. Let's just do something for now to make it empty, and then let's install this. And then I'll take basically this last example is the one I'm I think most interested to look at first. And get rid of those with that. What's that? I can get rid of that. Make sure it runs. Yeah, okay, we got our color. Let's try to like visualize this though. So let's also get some other stuff here. We can get rid of this too. Let's get some other things. I think we're gonna want a bitmap, we're gonna want a tile grid, we're gonna want a group, so why don't we just get it Displayio. We need anything beyond that? I mean, board, I guess, probably board. Yeah, let's start with that, see where that gets us. Boy, I don't usually just bust it out from scratch or just creating the tile grid and bitmap. Let's see if I can do it. I guess we'll need palette as well, but that's in Displayio. So let's go. So let's get display object so that we can use that. Let's just make a bitmap. Bitmap equals bitmap. We got to give it, I think, like the size and the number of colors, I think, probably. I don't know the order. I should get the stubs. Is it this easy? Oh yeah, somehow I have remnants of Python 3.8. That's right. I should be doing this way instead, though. I guess this is the best way now. It's 733. That should be good enough for what we need, though. Well, okay, it's not going to know bitmap, though, so let's do that. There we go. Okay, width, height, value count. So, I mean, we could just do the whole display for now. Display.width, display.height, value count. I'm just going to do value count. Value count. I'm just going to do what is, I guess, probably the max. But I don't actually know if that's the max, but that's what I'm going to do. We're going to make a tile grid. Tile grid equals tile grid. Tile grid's going to have the bitmap. Tile grid's going to have whatever else it needs, which is pixel shader. We need our palette first. Okay, palette equals new Displayio palette. Been up all night working on new rev of the TR cowbell. Figured out how to improve it. Knew if I went to sleep I might forget. That's how it goes sometimes. Hopefully you get some of it, hopefully you get it nailed down. Get some sleep sometime. Able to get the palette slicing to work. Oh, nice. Just to get item to confirm that it's object parsing. Nice. So you can essentially change subsets of the palette all at once. You can change indexes 8 to 23 of the palette all to blue at once or whatever. Do I understand that right? Tile grid, so it needs some sizes and stuff also. Width, height, those are in tiles. We're just going to be 1, 1. Is it a tuple? It says width, height. We need tile width, tile height. Those are just going to be the bitmap size, bitmap. We need anything else? XY00 are fine. Default tile is fine. I think that's all we need. We will need our palette here though still. We're gonna make the palette 255 also. I don't know if I'm gonna use all 255 right away, but we'll start there. We wanna probably do some stuff like this needs to get created back here probably. Might as well do this first, honestly, like before we do any of the rest of this. We need to basically put some colors in our palette. And to do that, we need to basically index, iterate through calling this function. Why don't we do, let's start with 100. Let's start with 100 instead of 255. And then let's just go for I in range 100. Do 101. Does this go to 1.0? Start with 100. I equals, this is where we're gonna call this thing. It will not be this, it will be I over 100. Ooh, not 200. More of those. I don't know, if we print our palette, is it gonna show us all the colors? Ah, whatever, we don't need to print it, it's fine. We'll see it in the screen or it won't work and we'll figure out why. We probably don't need this, we don't need this. We have our tile grid, we have our palette. Okay, we need to give this to here, so it's called pixel shader here. Make this better, kinda, not so long. Oops. I find every LED to be non-addressable 4-pin RGB. If you use the WS2881, control them, you can chain them together. Let's use LED animations, modifying every single step. Step switch is labor intensive. Whoa. Every LED to be non-addressable 4-pin. Nice. Full list slicing for start. Stop stride, including sequence reversal. Still need to include, delete, insert, and append. Nice. That's awesome. In palette, did you make that as a Python layer or C inside the core change? You have like a Python class that extends palette that adds that, or? That combined with your the tool that you made that kind of allows the chroma keys in a way, right? The tool that kind of allows you to pick out the colors that are near a certain color. Those two tools together are pretty sweet. Slicing and that allows you to like really do some super easy chroma key cut out the background type stuff. Basically turning non-addressable 4-pin LEDs. Oh, nice. I gotcha. So you've got the like analog 4-pin. I'm with you. So you've got the hookups and then you're connecting the controller chips to them. I think we probably don't really need much else. So technically we could just call display show on tile grid. Pretty sure that's fine. Honestly, I like having a group though. So I'm gonna make main group Displayio group in case we want to add more stuff. We'll show it. We'll also add the stuff to it. We'll wait forever so that it stays on the screen. All right. Yeah, okay. So far we have a bitmap object, we have a tile grid object, we have a palette which is filled with colors, hopefully. We've put our bitmap into our tile grid, we've put our tile grid into our group, we've shown our group on the display. We have not painted any pixels into our bitmap, so let's do that. What do we want to do? How big is the display? Let's go X. Let's go X. For X in display.width, which is also bitmap.width, so really we could just do bitmap.width. It really doesn't matter which one. We actually also do tile width on the tile grid too. Same thing there. For X in bitmap width, oh, range. Yeah, we'll need that, range. So we're going to loop across there. For each one, we're going to go for Y in range bitmap height. Here we're going to go bitmap XY, so is it actually XY or should it be YX? Weirdly, I'm not sure. And then this is gonna be let's just do it like this. This is probably not the best way to do it, but this is how we're gonna do it. Cur color equals 0. This equals cur color. Cur color plus equals 1 plus equals 1. If cur color greater equals length of palette, put it on back to 0. So it will repeat after the end. It'll make 100 colors. Hopefully it will draw them on the screen. We'll see. That's the wrong one. That's also the wrong one. Where'd our browser go? There we go. Nope, we got a crash. Something about palette. Display has no attribute palette. That's true. It's true. I mean, to be fair, that is true. Color buffer must be 3 bytes. And 13. Value error. 3 bytes. Add byte? Is it huh? X? First time or 4 0? So 0 worked. It's actually the second time through the loop. Python class that wraps palette object. Nice. Can't be inherited. Ah, okay. That one can't be. Okay. I can't extend that, but you have one that contains it that adds extra stuff to it. Nice. Bring your thought process and design considerations. For the sequencer, yeah. It also deletes the 23017. Deletes one of them. I see. Freeze up the second bus. Nice. I2C on any pin? Um, 3 bytes. This. Why would that not be 3 bytes? Does it not take hex into palette? Just remember the palette. So it gives you, this one I guess gives you just a number, or? Am I supposed to be doing just that for the? Does not want the hex there for some reason. I mean, when you enter it with code, you put it as hex, but maybe it doesn't want it as the result of that hex function. I guess that's probably a string, maybe. Is that a string? Is that a string? Hex, no, type, hex. Doesn't matter really, just something. Okay, I'm with you now. Okay, fair enough. So yeah. We don't want to put color. Yeah, and the first one worked because it was 0, and it just type coercion 0 string into 0 number. Color raw. This is what we want. Here we go. Could probably just call it color though. I mean, I suppose it makes sense there would be no function that returns a hex number, kind of, because how could it distinct between a hex number and a hex string, really? It's interesting, you can enter a hex number in the code and it understands it, though. Like, some part of Python knows that that's a literal type. Okay. Hasn't crashed. Has drawn all yellow. Okay, let's print palette. I don't know if this shows us the colors. If not, then I'll have to for loop it. Yeah. So we'll for loop it for... I just do color in palette? I don't know if that works. They're going to be numbers too. We will turn them back to strings in this case. Okay. Look pretty color-y. Color-y to me. So I think our palette's alright. We're looping through here. We're doing color, incrementing cur color. This wrong? Map XY, is that not how that works? Maybe it needs 2 square brackets. I need 2 square brackets. returns RGB compatible. Yeah, thank you. Comma in there. Okay. Let's make sure my X and Y are working right. Okay, override for X, Y or something. We could stop printing the palette, I think. Scroll way to the bottom. Dollar sign? Oh, we don't need dollar signs. This is not JavaScript. What'll happen? So, I mean, that's really slow now that we're printing, but it's fine to me. Let's go in 0 to 100. Oh. So was that not yellow? Was that like a trick that looked yellow? Yeah, I think I know what happened. We don't want to increment cur color actually until out here. This is indented too far. This needs to come back out. We're incrementing after every vertical pixel, which was not my intention. But I guess I didn't look close enough. I thought we got solid yellow. Did we not actually get solid yellow? Did we actually get like a really small canvas of red, green, yellow that looked yellow? Like old school TV, if you look really close at it. It looks yellow there. Oh, it is. Whoa, that is weird. It's like holographic kind of. I don't know if it will. So honestly, it looks like a camera artifact, but it's not. That's what the screen looks like. It has those weird lines that are, you can't focus on them really. So that's actual screen artifacting also. When I tilt it this way, we're getting all kinds of craziness. But the lines that are there, that are actually there, when you look at it, they look like that craziness. Now they look like the sun. Okay. Yeah, I totally did not look close enough. I thought this was just straight up yellow before. The diagonal lines totally give it away, the actual problem, which is that we did this. But this is like one of my favorite things about messing with graphic stuff is like when you mess it up, sometimes it looks cool. So that's awesome. Yeah, there we go. Okay, so we do repeat a couple of times. It does have black in the gradient too, it looks like. That's a neat effect. Okay, and then you could so like let's say you wanted to stretch this the whole way, right? Instead of repeat, repeat, repeat. So to do that, we could go how could we do that? We could I have a feeling that we could use the thing in here, simple IO. Is it simple IO? Simple IO? Map range? That's really not Displayio. Is it did I misspell it? Or is it a library? Maybe it's a library. Okay, library. I don't know why I thought that was a core module. Oh, that's interesting. If you fail once but paste it in, you can just import it right away. You don't have to restart. So this has map range. Map range we can use to do this, I think. So instead of... Okay. So it's no longer going to be cur color. It's actually going to be... You could just import map range only. We don't need the rest of this, actually. Change mode to continuous. Well, how do I change the mode to continuous? Is that in here? Mode light. Mode. Us. Us. I messed it up though with this. Let's change that to fix it. That's in the REPL. Nice. Okay. And then, so then I want to smear it bigger. So we're gonna go, like I could make more colors in between, but let's say I want to limit the number of colors I'm using to 100, but I want to evenly distribute 100 colors over how many pixels I have. So then we're going to use map range, which does what? Don't have it. I'm going to pip install it also just so I can see its arguments and stuff in the IDE. Okay, in, min, in, max. So in, min, and max are 0 and technically 99. No? 100. No. Technically 99. Yeah. Technically 99. Then I guess we're going to have out min and out max. That's going to be... No, this is wrong. Out is going to be 0 and 99. In is going to be 0 and the width of the bitmap. Yeah. And then the number is probably the beginning, is it? X? Yeah. The number is actually per color. What? Why are you mad? Int? Got float? Where? Per color? Not a float number. But I don't see floats. Expected int got float. Literal sub max any LE outer max. Oh, it returns a float. It returns a float. I see. I see. I see. I see. I see. That's not it. Ah, okay. There we go. Thanks, PyCharm. That should be all we need, I think. Not quite. Color. It shouldn't be color. It should be it shouldn't be color. It should be X. No. Yeah, X. It should be X. We actually don't even need color anymore. We do it this way. It's very slow. I mean, it's not very slow. I shouldn't say that. It's way slower than it was without the map range, I guess. Nice. What is the last color in our palette? Did we still wrap around some? Oh, this is going to make it way slower. We print once per column. Okay. Still much slower, but not as bad, maybe. Slows down. Some numbers are faster than others. We're approaching 99? 88? Okay, and it's finished. Yeah, okay. Okay. Because light mode includes black. Would filling with a vector IO line. I don't know. Good question. Yeah, I don't know. Maybe. We could try it. My suspicion is no. Because I think the time is not... I mean, for this exact iteration, the way it's written right now, honestly, print is like a lot of the time. If we take out print, it will run way faster. Faster, still not fast. It still takes a minute. I think the time is... I think the time is inside map range, probably. It's crunching numbers in there, and that I think is what's taking time. If we go back to the per color one, which just repeats instead of stretching, it crashes because I didn't comment it out properly. It loads much faster. I think doing all of this crunching is where we lose most of our time. So, and if we switch to vector IO lines, we would still have to do this crunching if we want our gradient to work the same way, in that we want to use fewer, well, two things. We don't want to repeat, first of all, because like if we're okay with repetition, then we just do it this way and it's faster. But if we don't want repetition and we do want to use a different width of our gradient than we have number of colors, because if we wanted only 100, let's say we have 100 colors, if we only wanted 100 pixels width, then we wouldn't have to scale any. We could just use exactly 100 pixels of what we have. So like this, we could just say 100 like that. And then we get our 100 pixels, and not sure exactly why the right half is red, but something made the right half red. But if we imagine like that 100 pixels, if that was really what we're after, then we get it that way. But if we want our 100 colors to smear over however many pixels the display has, or however many pixels we want in our bitmap, then we have to use something like map range. Now, map range seems to be operating on floats and things. I wonder if there could be a more efficient one that used ints, or I wonder if it would be worthwhile to bring the map range implementation into the core, see if it gets faster. Or maybe there's already something like that too, honestly. Maybe Microlab? I don't actually know. I'm not super familiar with all the different functionality in Microlab. Maybe there's a better way, faster way to do those things. Oh, this was a little while back, yeah. Okay. Is continuous what makes it wrap around? I should look more into the docs again, probably. What are let's just look at the different modes, maybe. Let's go to smear one. I do want to do the smear one instead of the repeat one. It takes longer to do. Smears across one. I'm interested to see the other types here. And maybe even well, no, I think in color table, that's probably the one we have to use for this kind of like 3-color gradient thing. Uplight. Iron? Stoplight. Stoplight might be, is that similar to the red, green, yellow that we're doing here? Visible? In color. Color table spectrum. Okay, those are the two. Light produces a blended color spectrum that mimics full wavelength of light representation. Doesn't wrap. First and last colors are not blended. Ah, okay. Default mode. Okay, I want to see light with the stretchy one though, because I don't think we had that. That's nice. So red, yellow, green, that's the order in here. Yellow, green. Okay. Yeah, that's a nice effect. So it's like, and I see where the blacks came from before light. So it's like fade up from black, fade kind of down to black in a sense. Although it doesn't wrap around like the thing said. It doesn't connect necessarily. Nice. Okay. I am curious still. I don't know if this actually does anything different, but even just as an exercise and a gauge in my own understanding of gradients or not, I'm curious to try using this algorithm from this page. So I'm going to try to implement this. But it does look like this does most of the same stuff, I would think. Is it possible to have the edges tend towards white instead of tend towards black? Or is that not actually what's happening? I guess to my eye it looks like that, but I'm not certain that's what's happening. Smooth gradient looks good. End color table is faster. What are we on? We're on end color. I think we are on end color table. Is faster than color table, faster than, not sure. Gamma 6. Oh, maybe this is actually to do with it. Gamma. Let's read about gamma. I think that's something to do with brightness, right? Sorry, I don't actually really know anything about color theory or visual theory or any of this stuff, to be honest. Gamma. Oh, it doesn't highlight all of them. Interesting. 0 to 1. 8 is tuned. In color. Oh, faster than in color. I gotcha. I see. In color is this one versus in color table. This one. Actually, I didn't notice the difference before. Table. Oh. Nice. Okay, so you have one that's got a trade-off already. It's got some kind of lookup table inside of it, so it's got some pre-calculated stuff that you could store in memory, and it helps do some of the calculations quicker. Nice. I see. I still think a lot of our time, I think generating that, I mean, we'd have to put prints or something. We'd have to actually print some values. I still think most of our time, though, was in here. Honestly, I think this is not taking that much, most likely. Set it to 1, see what happens. My style of coding. I like it. Let's try it. It's not, it's like, I think it actually maybe accentuated the darkness a bit more, and I think, let me put it back. Let me actually get a good, okay, get a good comparison here. It's like, I don't know I definitely don't know the theory or the technical like thing behind it. What it looks like from my kind of untrained eye, and the best way I can describe it is 1.0 versus 0.6. 1.0 is like, has like JPEG at artifacting almost. Like the bands of color are more visible as vertical bands, Whereas this one, they run more smoothly together. I can't pick out as many distinct vertical bands of color in this one. I'm curious to try a lower value now. But I imagine this probably depends a lot on the display, right? Because the doc said it was tuned for TFT. It might be a thing that's like kind of different for different displays. Oh, interesting. Okay. So this one kind of makes it less blurry, less like the gradient is less accentuated. It's more kind of rigid. I do think so far the 6 looks the best on this screen, at least. To get white boundaries. Oh, duh. Yeah. Good call. Yeah. Now we're thinking with code. The other thing you could always do too is I don't necessarily have to use the entire range. I could also do something like, especially because we have map range here, I could do something like 10 and like 99 minus 10 or something like this, right? We could cut off the edges, kind of bring out the middle of the range a bit further and discard the outliers. Nice. Try a little bit further. I do like the white effect. I just want to minimize the white bars a little bit. I like the trending towards lightness though at the edge there. Yeah. I like that. I'd maybe make the red a tad wider if I could. I don't know, is it as simple as just adding a... If I duplicate red, is that... I'm probably not cutting off the edges properly either. I'm probably cutting... I probably have an off by 1 error in the way I'm cutting the edges. I would not be surprised at all. Ah, there we are. Yeah, we can get a nice thick red like that. And then I do think the edges are not quite cut the exact same, so I'm just going to bring that to 11 there. Kind of aiming for like most of the whole screen, but trending towards white, just right on the edge there. Nice. Could maybe come up just 1 or 2 more here on the front side too. I don't know why I'm interested in this specific gradient, but what I'm aiming for. Yeah. Nice. Okay. I am gonna go and copy paste Seagrover gradient. Maybe Seagrover gradient test, I should have called it. But that's all right. I'm gonna keep some of this stuff because we're actually probably gonna end up with very similar things going on. Actually, to start with, I'm gonna look over this thing. So I'm gonna kind of go ground up, which is, we're gonna do, I think, a basic 2-color one first. So tuples of RGB versus hex triplets we're pretty familiar with. But one thing that is a bit different about, so there are Python implementations of this stuff on this page, but these Python implementations are CPython, not CircuitPython. And they're actually operating on hex colors as strings, which I'm not sure that that's what we want. We may want to change these to return numbers, and then you would pass it to the hex function in order to get it from a number to a string. because the numbers will be easier for us to work with. Although the tuples would be fine as well. I think a lot of our stuff takes tuples too. I see. Every TFT could be different. And the game will let you kind of tune it to your specific one. Acting like dithering in a way. One trick. Horizontal gradient. The glass buttons Apple first introduced. Nice. Yeah, I did a 2 instead of 1, but we did get pretty close. 0.2. So I am gonna start this as another file. Maybe I'm just gonna call it gradient helper. I don't know. I don't know for sure if we'll actually get it working. If we actually get it working, we'll worry about what to name it and if we're gonna publish it, and if it even does anything different than Seagrovers, honestly. Partially, maybe this is just an exercise and it results in the same thing that already we have, and then the answer is probably just use that one instead. But I'm curious to go through the exercise of finding this page, which has the CPython implementation, and trying to get it into CircuitPython, seeing what hurdles we run into and what problems we need to solve. And I am thinking the string thing is probably going to be an early on one that we want to potentially change. Linear gradient. Rid of white. And 2 hex inputs returns a dictionary containing the desired number of hex colors evenly spaced between them. Okay. In a list of RGB sublists. So this may run. If I say it's written for CPython, I don't necessarily see anything off the top of my head that doesn't look valid for CircuitPython, but just it's going to be outputting these strings of hex, which are not, the strings of hex don't do much for us. And if we could skip strings and just go straight from tuples to numbers, presumably we use less RAM, I would guess, right? Let's go colors equals linear gradient. So we go start hex, finish hex, and it does want strings right now, so I will give it the strings to start with. Let's say we were gonna have red and blue. So we'll see. Gradient helper, though, we should put that in code. Yeah. 5, 7, 8, 9, 10. So it gives 10 colors by default. Yeah, it gave us kind of a bizarre format we have a dictionary which has a hex key, which is a list of strings. Then we have a B, G, and R key, which are each lists of that one channel's value. Interesting. Okay. We did get colors, though, which is good. So, and then I assume 10 must be the default in here, probably, right? Is there a... Yeah, n is 10, linear gradient. We didn't pass anything different, so we just got 10. We go 20 here, we would get 20. Yeah. All right. Okay. So I wonder, maybe we should just... I wonder if we could make this operate only on tuples? Or should we really strive for operating on, like, int hex, like 0x? Let's look at the actual code here. So we get our hexes from the user as strings. We are just immediately calling hex to RGB, which is giving us back those... It's a list in this case, but we'll call it a tuple for all intents and purposes. It's not a list that's ever going to be more than 3, so it's giving us back those tuples essentially. RGB list starts as a list with start color in it. Iterate over n iterations, starting at 1. Calculate some stuff. Three times. This is probably technically really the math that's in this. I don't quite follow all of it, but I'm guessing this is basically the Python representation. And then add it to our list, and then at the end it's calling colordict, which takes a list of RGB sublists. RGB list. What does that actually look like? I mean, that's pretty much usable for us. That's pretty much usable for us. So we actually probably don't need to... I mean, I think we just stay in tuples. Let's not worry about hexes for now. Maybe hex could possibly be more efficient. I'm inclined to believe that a hex representation of this color takes up less memory than a tuple, but I don't actually know that for a fact. But since we support tuples, we may as well start there, because it looks like that's actually going to be really easy. So we could just not be returning colordict and instead just return color list. I don't really need the dictionary. Yeah, frankly, the docstring... The docstring doesn't, like, match up with what it was doing anyway. Because it was talking about the colordict thing. We don't really need this. You probably don't need this either. Lowercase? Being used? No. Okay. So let's try to use this one with Displayio the same way we did. And then this is just linear gradient. There are the ones that do the multi-steps as well. This page kind of progresses in complexity, so this is just the most basic one. We'll want almost pretty much a lot of the exact same things, honestly. Just generating our colors a bit differently. Should we generate 100? Could start with 100 to keep it kind of similar. Converting RGB bytes to a composite integer. Oh, nice. So this would be a composite integer. Okay, RGB bytes. This would be let me put it like this for now. Let me just comment it for now. We'll need we would be taking a tuple, I guess. Def tuple to hex. I don't know, it feels weird to call this hex and call this hex. Mine's going to be a number and not the string. I think ultimately we're going to try to make this not take the strings anyway, though. So I think eventually we're going to be not having strings. So I'm happy to call this hex, even though it represents a different thing than what we already called hex in this code since we took it from the page. We'll do this, though. Tuple to hex. So tuple color comes in. Hex color goes out, which gets done like this. See, Grover, thank you. Red, green, blue is actually just going to be tuple 0, tuple 1, tuple 2, if I understand correctly. This would get us to a hex. So we could, a hex number, importantly, not a hex string. So that could ultimately allow us to skip, potentially even skip tuples altogether to try to save some additional memory. I'm going to try to get it to work with tuples too, though, just because, like, we're most of the way there, I think. We'll do 100. We'll have our 100 here, have our 100 here. This won't be spectrum anymore. Instead, it will just be, I mean, honestly, we just have colors, right? I think we could just loop over colors and add them to palette at this point. And I think they just work. I'm not sure. We'll find out, I guess. Loop. Let's go for color in colors palette. Oh, we don't have I. Fair enough. For I color in enumerate colors. Okay. We want to do the map range thing this time. Let's start with the simpler one. Nice. So the smearing works basically the same way. Should. Just need to import that. Yeah, same thing here. We take way longer to do this. I think map range really is where we lose our time. But there we got a nice linear gradient going on. And that is looking pretty good. I'm liking that. I am liking that. Eventually what I may do is display shapes doesn't have gradients, does it? It has outlines and fill color, but it doesn't have gradients. Display shapes? CircuitPython. GitHub. Do gradients, does it? No. It might be nice to have these allow gradients. Might be a nice way to utilize this functionality. That way, like so far we're good. We're generating the palette of the gradient, but it might be like a lot of users are gonna want like, I want a rectangle, this shape with this gradient from this color to this color. Eventually we could maybe even get into more fancier stuff, like this is a, you know, horizontal, vertical, whatever, right? This is, but maybe we could have diagonal, or maybe we could have like the center burst one where it goes out from the middle or whatever. Those are kind of like, they depend where you paint the pixels, perhaps a bit more than where, like how the colors are in the list. If that makes sense. But let's start nice and basic though. We got our linear going pretty good. That seems to work pretty much how I was expecting. Let's try to get rid of the strings though, because we do still currently give it that string here. So let's take a minute here and see if we can't make that better. So, I mean, to start with, we could be having tuples here, right? This could be white, which is this. Start hex is required. Well, we wouldn't call it hex anymore, would we? Start, I guess, just finish, start and finish. Color. We want to say color? Color? Color. And then, I mean, technically we could just use start color instead of S, but let's do this for now just so we don't have to change as much code. And then if we passed it tuples, this would just do same thing now. So let's change it up. So we did blue and red before. Let's go like green and yellow. Let's go like Sprite. Green and yellow. So 0, 55, 0. 55, 255, 0. Nice. Got the old lemon lime going on there. Okay. Good. So now we don't have hex strings in the mix at all. I think I'm just going to delete this for now, and like eventually, if I get all this working, if it's actually worth having this, if it doesn't, like if it is not something that's already covered under Cedar Grove's library, which is still possible, I'm not sure. If I ever get to the point though where it makes sense to publish this, I will just come back and actually make proper doc strings for it. We're having some that are missing anyway. We're having some that we're not going to need. We're not going to be doing the strings. There's a lot of stuff that's going to have to change in the doc strings and the comments if we publish it ever. So I'm just going to delete the second half, but not bother writing it out for now. So now we're close. Premium gradients. Yeah. The more fancier, like out from the middle, or the squares, or the diagonal lines. Yeah, all kinds of interesting ones that you can do. So, I mean, this should work pretty similarly in reverse, should it not? Or I guess this probably exists somewhere, right? Should I search instead of try to write it? Bet you this probably is just there. Hex color tuple to, so Python color tuple to hex number. Wait, no. Other way around. Other way around. Python color hex number to tuple. Oh, that's hexadecimal string. I won't dig too far. I think we can actually just convert what's there. This looks like strings also. Okay, I'll just give it a shot, and if we fail, then I'll look further into running a better resource. But I think we can just go kind of opposite of what's here, right? Nice algorithm. Better suited to this than RGB spectrum tools. Oh, nice. So I think we can just go, basically just do this in reverse, right? Def hex to tuple. This is going to take a hex color as a number. It's going to be returning a tuple. I don't know. We might want to declare it first. I don't know. We'll see how gnarly this gets. But basically, we can kind of like just use these in the opposite way. Is that right? Am I thinking about that right? So like if we did like R is that makes sense. Would it be the other way, or would we flip these around maybe? Let's just start nice and easy and go print R. See where we're at here. Let's also import this as hex. Oops. I don't want to import call it. That doesn't make any sense. Hex to tuple. So then let's just go call it right here just to see what it does to tuple. We'll say let's go red. We do all the way red. Let's try like not quite all the way red. Start with that. We'll try some different ones. 187. So do we that sounds actually maybe right. So do we get 255 if we do this? We do. Okay. Okay. So that got our red, so then green is going to be similar, but it's basically the 8 there. Blue. I'm not sure what to do with blue, though. Blue's going to be a weird one. How do we get the remaining? Do we do 0? It's unlikely, right? Unlikely. Maybe it's 1. Oh. Okay. No, that was wrong. Interesting. Okay. Now we get to watch Tim fumble through bitwise. I would assume it does not, it cannot just be back to this way, I don't think, right? That doesn't make any sense. But we need to somehow shift, would we need like 800 or something? Works for red, but green and blue will need AND masks. I see. That's probably the problem we're running into with here. AND masks. So we would actually need something like work like that. I don't actually know how to do it. Python and mask. Let's look it up. Python and mask. This is a masked array. I'm not sure this is what we want, really. We want like bitwise and. Single ampersand. I was close. I don't know why I was thinking it was two. Bitwise and. Would we then, so do I have it right? We would basically bitwise and something like this to give it the, basically help it figure out the right bits? No, that's not quite right, but it's maybe closer. Oh no, we had the same thing the first time. It'd be maybe, I don't know how order of operations work. Oh, same thing there. Green color. We need to bitwise, or I mean, we need to end the color before the shifty deal. Okay. Zero. Let's make sure it's actually working on green before I do blue, though. So let's say 55 there. Okay. And then let's do just to make sure it's like partway working too. Okay. Sweet. Thank you for the help, by the way. And I think I can get the last one from there. So this would be the same thing, but we would be having the bit mask like this one. So, and then we probably don't need this. This probably doesn't actually do anything, does it? It would. We would need that. Let's try it like this. 0. So that's actually what we have. So let's do a FF there, make sure. Okay. Sweet. Thank you. Yep. Appreciate the help. So now we just need to not print it, but return it. Then we now have tuple to hex and hex to tuple. So let's say, like, internally, let's say I don't want to change this. Let's say I want this to keep operating on tuples internally, but let's just say I want it to return me a list of ints. So, like, internally, that's fine. It's going to use a bit of extra memory. Sure, we could probably squeeze out more efficiency by making it do hex internally, but then we are essentially going to be having to put our own functions in this, which is already, like, on the edge of my understanding. You know, frankly, I don't necessarily understand the function here. I'm sure I could probably poke and prod my way through it, or perhaps get help from a kind soul to get through it. I think what I'm fine with, though, is like, that's cool. Operate on tuples internally, but just turn them into hexes to give them back to us. And also, I think we want to take hexes here. So what we're going to do is this is now actually going to be a hex, white, like that. And then S and F, so it's a good thing we left S and F here, because what we're going to do is hex to tuple on start color and hex to tuple on finished color. Right, like that. And then I think it should work, right? We'll need to change these out. Let's pick a new gradient. Let's say something interesting we could do? Maybe let's do like green and pink, let's say. So we have green actually. I'll switch it. I'll switch it to the other side though. Let's go pink here. Green over here. got something unsupported R shift for tuple int. 12 is when we made our gradient. Okay, yeah, this one no longer prints, so this we don't actually need. That was just testing. Upper linear gradient, hex to tuple. And here, hex to tuple. This was still a tuple somehow? Follow that again. So 29 inside linear gradient. No, 23, excuse me. 23 called hex to tuple here. Oh. Yeah. Yeah. I changed the colors to tuples, but we actually changed it to mean to want hexes. I was too concerned about the colors instead of the formats. So pink to green, but we need hexes this time. For gradients, it's easier to work with RGB separately when calculating the overlap. They act like separate spectrums. There we go. We got a nice pink to green going there. And one of the nice things about this technique is we can actually have less. So like, let's say we're making some like, I don't know, like, you know, 8-bit inspired graphics or whatever. Like, let's say we want to minimize the colors. Let's say we want a gradient still, but we don't want it to look like modern, smooth, blurry, like clean gradient. Maybe we want it to look a bit older with drawn by something with fewer colors, let's say. So you could maybe say, let's have only 40 colors in our gradient. Let's have only 40 colors in our bitmap. And only 40 colors in our palette. We should probably make a variable with this if we actually wanted to change it. And then, in fact, why don't we just make a variable? Color count. Be the change you want to see in the world, right? Let's make the variable. Color count there, colors, map width. So that's going to be x0 bitmap width. Yep. And then we're going to be changing up this stuff. Oh, this would have made our gradient look a bit odd, right? We actually cut the beginning and end off here, didn't we? Yeah. Well, that's all right. So what we really want here is actually just going to be 0 again, and then max would actually just be color count here. Color count here. Yeah. I think this also tells us that map range is where our time is going. Since this one didn't really get much faster, even though it's less than half the number of colors. But the number of map ranges doesn't change because we're still doing the same number of pixels. So we have to call the same number of max ranges, but less colors this time. And so now we have more of that kind of vertical banding. Like if you look at this, you can kind of see the sections that represent each color. And you could even go further, like if we drop that down to 20 or something, eventually you'll start seeing like individual kind of columns. Yeah. Like that one, you know, the camera doesn't quite necessarily pick it up all the way, but we've got like these little individual, you know, 10 or whatever pixel vertical stripes now that are the different colors. And you could continue on down from there. We got a nice blocky looking gradient there, which might be what you're going after, right? Sometimes that's what you want. Okay, it's looking pretty cool. I'm digging that. Okay, so we got a linear gradient. Let's take a look at what else we have on this page. So I will say part of the stuff on this page is the way that they visualize it, which I won't be doing. They're visualizing it in, I don't know what this is. If it's is this Matplotlib or whatever? It's something is drawing these like graph chart sort of 3D, but actually a 2D picture with perspective. I don't know what is actually drawing these things for them. I haven't looked into that portion of the code as much yet, but we're not doing that bit. You know, obviously I'm here for the CircuitPython integration, so I'll be just continuing to visualize with Displayio instead. A polylinear interpolation. While one linear gradient is fun, multiple linear gradients are more fun. I see no lies so far. Taking linear gradient and wrapping it in a function which takes in a series of colors, we get the following gradient function. Also included a function for generating a random hex color, so I don't have to spend time choosing examples. Oh, I don't know. I kind of like spending time choosing examples. That's all right, though. Okay, and so this one is a polylinear, so this one allows you to do more than 2 colors for inputs. But it's still, if I understand right, it's still equally spaced. So you're going to give it 3 colors, or 4 or 5 or 6 or whatever, right? You're going to give it a N colors, let's say, and you're going to get back a gradient that's equally spaced between all those colors. I believe that's what's going to happen. That's kind of a hypothesis at this point. It's yet to be seen, but and the graph on this one is a bit weird. It's unclear to me if well, I don't know, just like I can't wrap my brain around the line. It looks like the line has meaning, but I don't know. Can't wrap my head around what it is really. Multiple moving gradient sounds fun. Down with that as well. So this one will need to do a bit different because it's probably going to be the same thing where it's actually expecting those hex strings. Oh, no, maybe it's not actually. I don't know. Now I'm not sure. Maybe the deal is that they are equally spaced, but equally spaced doesn't actually look as good as you want for some colors, and so maybe using the Bezier curving makes certain colors look better by not being equally spaced, essentially, by introducing something that's non-equal but just looks visually better to our eyes or our screens or whatever, right? We will do this one first. They don't actually have sample code though, I guess, but this must be expecting. It must be expecting the hex though, I think, right? It's also doing the whole dictionary thing, which we don't want. Well, we're gonna have to look at it and see, actually. We're gonna have to look inside the dictionary and figure out maybe in out. In out? No, that's number of out. I don't know. We're gonna have to look at the dictionary. All right, let's just call this one and see what it does. Polylinear gradient. Polylinear gradient. So it takes a list. Let's give it 3. We'll go nice and easy. We'll just go red, green, blue for now. And I'm assuming it's gonna want these. Two positional, 1 were given, so we need n also, which was the number of colors we want to generate. So we'll just use color count, and I'll move this to be below. That's basically what that variable is for. And so 10 will actually be kind of tough with 3 colors, I would assume. We might need to bump that up a bit, but can convert int to string implicitly. All right. Graph is just showing linear value changes between separate RGB color spectrum sans gamma. Yes, I recognize all those words as belonging to color, but don't actually have like a what does that mean inside my head, really? Or any way to visualize like I couldn't really necessarily answer the question of like why is this one here and this one is here? I know that it's something to do with the colors and I see the values here and I assume this is higher red value, I guess, but the 3D nature of it is actually kind of difficult for me to visualize the colors as a 3D plot and what it means to be at a given point within that 3D plot. It is interesting and it does look pretty, I will give it that, but it is not something that fully like clicks in my head. What did we get here? 48. Cannot convert int. So probably we probably broke it by making our thing return other stuff. And actually, we didn't get all the way through this, did we? We are still returning a list of tuples. Yeah, why don't I finish what I was working on, which is making this return hexes. And I got jumped onto the next one before we were done. And then we'll have to adjust polylinear to account for the fact that we changed linear. Might make it kind of difficult. We might need to bring back the original linear gradient so that we can study the interoperation between polylinear and linear to figure out the right way to call it with the new format. But we'll cross that bridge when we get to it. Start with, though, let's look at our list. I'm pretty sure we should be still having a list of, we're just going to be having the list of tuples, which will actually be lists. Except the first one is a tuple, the rest are lists, which is interesting. We could make those tuples. Let's do that. Probably just like give it one of these numbers instead. Then that should just be a tuple now for all of the rest of those. Ooh. Now they're like generator. I mean, so I could do this and it will work, but that doesn't necessarily feel right. I don't know. Guess maybe that's what we do. So then we would just append the tuple to hex of this. Means now the first one is wrong, so let's do that. The first one we would do here, actually, tuple to hex also. That one. Okay. Now those are numbers I assume they are right. We obviously we're not looking at the hex representation, so it's a bit hard to tell. But yeah, on the screen it looks fine. Looks the same as it did a minute ago, so. Cool. All right, now we're taking hexes, returning hexes. Perfect. In the grand scheme of things, I suppose we might want to do either because a lot of Displayio actually supports either, which is why I was able to actually make that work before without having made the change, but I think we'll keep it for now. Start taking a look in the polylinear now. So it's wanting Boy, yeah, it's wanting that dictionary thing. Which is long gone. We definitely no longer have that. Once it got the dictionary, it was going if length of colors is greater than 1. Seems odd, but I guess that's a special case for a single color. Or column in range starting at 1, length colors minus 1. Next equals, and it's calling linear gradient again on colors call plus 1. It's so it's basically actually pretty simple. A lot simpler than I would have expected. It's basically just starting with a linear gradient from the beginning of your list of colors to the end of your list of colors, and then stepping through each color in the middle and like inserting a gradient from the current one in that beginning gradient to the current one in the actual list of colors. Is that right? Let's get the original linear gradient back so we can try that out. I think I'm understanding it, but I'm not % sure. I don't have color decked either anymore, so I'll get that too for now. Let me catch up here. There's a gradual line between each color, stopping point. It would be interesting to convert the results list to a palette and apply a bitmap of a gradient shaded shape. Convert the result list to a palette and then apply to a bitmap a gradient shaded shape. Not sure what you mean, a gradient shaded shape? Could the gradient shaded shape be created algorithmically? Sure what you mean. If you just mean like make a rectangle that has the gradient as the background, like the fill color, would that be a way to create the fancy premium ones? I'm not sure if I'm understanding, but I think it's possible for it to generate the shapes for you somehow. Like, so like right now we're telling it we want a gradient of this many colors from this to this, but we could build on top of that and say, I want a rectangle of this size and shape at this location that's filled with a gradient of these colors with this many colors in between. And then the next iteration of that would be to instruct it like, I want a vertical gradient or a horizontal or a diagonal or a sunburst from the middle or whatever. All right, we're actually missing that helper one as well. I got rid of a lot of the old code, much all the old code, in fact. Let's get that stuff back. Okay, so this is what the first thing returned. Which makes sense. It started on red. Green is in the middle, somewhere around here. Blue is on the end. So the list that is inside of hex at the end of calling polylinear gradient, if we had that same list as numbers, that is essentially what we want. Okay, I get it. It just clicked. So we give it 3 colors. We tell it we want 10 total colors in our output. Well, in our example, we gave it 3. Obviously, you can give it any number. We gave it 3. We told it we want to get 10 colors. So what it does is it basically divvies up 10 into 3 equal parts as best it can. It won't be exact. It divvies up 10 into 3 equal parts as best it can. The first part, it gradients from the first color to the second color. The next part, it gradients from the second color to the third color. There's actually only 2 equal parts, not 3. I messed that bit of it up. But if we had 4 colors, there'd be 3 equal parts. Basically, it's making a linear gradient between each of our input colors and then putting all of them together at the end. So this is not, yeah, earlier I said between the first and last, and that's not actually the case. This is just the linear gradient between the first and the second. And then after that, we start getting linear gradients between the second and the third. Then we would go between the third and the fourth and the fifth. We would get linear gradients between all those colors, making sure that we have a maximum total of 10 or whatever n was, because we divvied it up at the beginning into that many equal spaces. Okay. So what is in out in our case? Is that 3 or? Five was not the number I was expecting. Are we still on 10 count? How many numbers are it? 1, 2, 3, 4, 5, 6, 7, 8. It actually gave us 9. 3, 4, 5, 6, 7, 8, 9. Yeah, it gave us 9, not 10. Five is not at all what I expected. Where does 5 come from? So this is... We're passing 10 right now. 10.0 divided by the length of colors, which is 3. 10.0 over length of colors, which is 3, minus 1, which is 2. Okay, 5 makes sense now. Why 5, though? So mathematically it makes sense, but not theoretically. Like, how does 5... 5 seems completely unimportant to me for No, okay, 5 is the middle, and we have 2 equal parts. Yeah. Okay, it'd be 3 if we had 4 colors. 3-ish, let me say 3-ish. I don't know if it'd be 3 or 4, but let's say after blue, we go to yellow. Those are 3 now. Okay, yeah. That is the size of the equal parts, and I was just still stuck on 3 equal parts instead of 2 equal parts. We probably actually get 10 this time. 1, 2, 3, 4, 5, 6. No, we got even worse, actually. We only have 7 colors now. We're getting less and less colors. Does it talk about not giving you the number you asked for? There's a list of colors forming linear gradients between all sequential pairs of colors and specifies the total number of desired output colors. Does not really mention much about not giving you back the number you asked for. But let's keep stepping through the logic. Morning, Dishipu, how's it going? Got a shovel. Shovel the walks. We'll catch the rest on VOD. Fascinating session today, thanks. Yeah, nice. Have a good day. Take it easy. Shoveling don't work too hard. Stretch out, all that stuff. Sometimes I go and shovel it in the morning, and it knocks me on my ass if I don't. I do it too long, so just take breaks, drink water, do all that fun stuff. I'm sure you will. Stay warm too, but not too warm. Just part of the problem. Okay. In, out. The number of colors per individual linear gradient. Okay. So, but if we added, so we put to the 4 colors, that means we should have 3 individual linear gradients. If each one has n out, which is 3, that means we should have ended up with 9. Why'd we get 7? So we start by making gradient dict, which is getting the gradient between the first 2 colors and is getting it to be this many long. So I'm going to take us back to the 3 color example just to hopefully make it simpler. So this is our math here. Between 0 and 1, first 2 colors, we're going to get a gradient of 5 out of this. If length of colors is greater than 1, it is. We have 3. For column in range 1 to length of colors minus 1. So in our case, that's going to be range of 1 to 2, which means iterate only once, which makes sense because we have our first half here. We only need to generate our second half, basically. So we basically, yeah, we're going to iterate once. We say next. This is going to be our next linear gradient. This is going to start at call, which is at colors call, which is our, in our example here, it's our second color because this was between first and second. This is now going to be between second and third. That is also in out, which is making another linear gradient of size 5. Looping through keys. Gradient dict. So this is the dictionary we first generated back here. Okay. We're going to keep modifying stuff in this. We're going to say for each one of these keys, we're now going to be just plus equaling. Okay, so hex currently contains a list of 5 colors. We're plus equaling a new list of 5 colors, although I suspect this is cutting the first one out like this says to avoid duplicates. So we're actually plus equaling 4 new colors instead of 5. But the first one of those 5 would have been the last of the ones we already had. So that's why we got 9 before, and I guess that's also why we get 7. You get kind of -1 for each input color. We had 3 input colors, we got -1 for each. That took us down to 7. No, we had 4 input colors. So it's 1 for each equal segment, not each input color. Excuse me, is what the -1 is. Essentially, each time you go through this loop, you're losing one of your desired output number of colors. +1 from the beginning? No, I don't know. I'm not sure the exact formula, but you lose like 1 per because of this, the way this is counting, essentially. I follow, but it's not crystal clear. Like, I get it, but it's not, I don't have the exact numbers in the right spots, but I think I understand. So, oh, camera just died. We'll see if we need it. So if we wanted to modify this to work on our version, which does the hex lists and takes the hex numbers, we could basically just do a very, very, very similar thing. This will not be gradient dict. This will be, let's just call this out list. Let's call this out list or out colors, out gradient. Gradient out. Let's call this gradient out. And I'm going to shrink this. I'm going to shrink this. I'm going to shrink both of these, and then we're going to come back through and delete all of these here in just a few minutes. But for now, I'm going to keep them in case I need to reference them. But to start, we're just going to name this back to gradient out. We're not going to do original anymore. We are just going to pass it colors 1, 2, because that's going to be a list, so that's fine. We probably should have a check here. We have a check down here to check if length of colors is greater than 1. But here we're actually hard coding 0 and 1. This would crash if you passed it a single color, I think. So probably that should be up here, but I don't want to change too much of it, like, while I'm also trying to make it work under a new way. So I'm just going to leave the logic alone for now and change only the bits that need to be to work under my formats. That's going to start us out with a list of the first equal portion of our gradient. So if we're continuing in our example of the 3 colors there, that's going to start us out with a list of the first half of our gradient, because we have 2 equal portions. Although they're not actually equal since the first one has -1 color. But we have 2 equal portions and a color in the middle is really what we have. We have 2 equal portions of 4, and then we have 1 color in the middle. But it's actually generated as 5 and 4, so that works. That's going to be our list, so we should be able to just add to our list basically the same way we did this. We just won't do, we're not doing keys, we don't need that, we're not looping, we're only tracking one output thing now. We're not having like different things like this did. We're just going to say gradient out. Yeah, no key, no more of that. Just plus equals, next, and then it's just next, right? Next, and do the cutoff 1, I guess, right? Do lists plus equal like that? I think they do. This is L2 then. Yeah. No, plus equals. Let's say L plus equals L2 print L. Yeah, okay, perfect. Yeah, that goes in there. That should be gradient out. I think that's actually all it takes. Just we will need to change these to hex. To numbers hex instead of string hex. And we haven't painted it on the display yet. There's nothing to see, but we should hopefully get it printed. Nope, not subscriptable. Or you can use extend to be more explicit instead of the plus equals. I gotcha. Extend, you can pass it another one. What do we int object isn't subscriptable. Line 12. 102 polylinear. Something we've done wrong in here. Colors. 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 Colors should be a list. Only not an int. I got our 5. Print type color. Colors? Excuse me, colors. Yeah, it's a list. Is it still a list in here? Because the only thing subscripted is colors. Well, no, okay, it's inside though. It's inside. Okay, okay, I'm with it. I'm with it. Okay. Oh, this is original. Shoot. Shoot. All right. That's probably it. Fine. Okay. Perfect. What is all of this? Let's get this back off. We don't need that for now. Right. So this is our polylinear gradient right here. We ended up with 9 colors. 9 colors instead of 10, but that's fine. So that one's just testing for now, but we could actually use it by doing colors here. And then the camera did die, so I'll have to restart this. And refocus it also too. Put the light back on if we want the light. Okay, so we ended up with 9 instead of 10, which is why we have the one empty slice there. Everything else is still assuming 10. Let's bump it up, though, to a bigger number anyway, where that's going to be less apparent. Let's kick it back up maybe to 40. Yeah, there we are. That's like a nice... we would still have the same thing. There's still an extra column of black over there. I guess, yeah, I mean, it's difficult to, I mean, you could predict it. If I went back and figured out the actual correct algorithm for knowing how many colors you're going to get based on the number you gave it and the desired output, like there is an algorithm that will tell you the number every time, but, and then if we had that, we could put it in CodePy in our map range here instead of color count, and that would make us equally smear all the colors we got, even if they aren't the number we asked for. Sweet. So we got our polylinear gradient going, and this is just by proxy of using linear gradient. This is already returning our floats. I mean our hex numbers rather, not floats, but hex integers. So that is working good. I think I do like the extend idea there on that one. Make sure that does the same thing. Because, yeah, plus equals on the list, I don't think, like, I tested it out and it does do what it's supposed to do. I don't really have that committed to memory, though. I think I'll wonder, if I was looking back over that code, I think I would wonder if it behaved like that again. You know, I saw what it behaved like right there, so if it's anytime soon, I'll probably remember, but if it's like a year down the road or whatever, and I tried to look back over this, I would be like, I'm not actually sure how that behaves. I'd have to either test it again, or who knows, maybe by that time I just have it down better and I would know it, but... And then this should work for arbitrary lists too, so we are giving it 3, but we could just as easily give it 4, 5, 6, 7, 8, 10, 20. Should just work with whatever we throw at it. Now the number of output colors starts getting weird, like the desired colors or whatever, just like we've been talking about, but we may be off by a couple there at the end, but you know, you can just arbitrarily kind of give it a any colors you want there to generate these gradients this way. I wonder if we could compensate for the -1s. Or maybe we could, maybe there could be a Boolean for exclude duplicates or not. Okay, we are to the point where I can delete all these. We're probably going to want them when I go and implement the next version though, right? I bet we probably will. So here's what I'm going to do. I'm actually going to cut them and I'm going to put them down here. Because my guess is we'll probably want, there's one more section on the page, I think, the Bezier one. Nonlinear gradient Bezier interpolation. Okay, here's our, yeah, it is matplotlib for drawing. But this is the last one. This is a Bezier interpretation, Bezier gradient. And my guess is it'll be relying on some of this stuff. So we'll keep all that stuff down there. I'll probably use it later. If not, we'll delete it. But I do still want to do the Bezier one. I don't think I'm going to do it today. I think I'm pretty close to wrapping up for today. But I definitely am feeling like this was successful. I got the basics of it down. I understand the code that's on this page enough to actually be able to convert it to CircuitPython. With help, again, thank you, C. Grover, I was able to get it converted to actually use the hex numbers instead of strings and tuples and all that stuff, so I'm feeling pretty good. I want to see a couple of more of these, so I'll play with a few more pretty colors, and then I think I'll call it a day for now. If anyone has questions or comments or anything, now is the time to get those in. Otherwise, play with this for a few more minutes and then be wrapping it up. Ooh, I do like the pink on the end there. Teal? Put teal as the last one? All right, let me see. Ooh, I do like the teal there at the end as well. Let's see, can I search these? Any other? Okay, this looks pretty cool. What's Python though? All right. I think that's going to do it for me for now. Let me see. So thank you everybody for watching. Nope, been listening, redesigning my board. Pretty rainbow day. Yep, lots of pretty rainbows today. I don't know exactly when I'll be back for sure. Definitely, I mean, I'll definitely be streaming Monday sometime, but possibly before then. I do still want to work on the Bezier curve one, so I think that's probably the next thing I'll do on stream if I do stream before Monday. But you know, like I said, I'm not sure. We do have a couple of folks on watching via Twitch. So what I'll do, I don't normally raid folks, but I'll do the raid on Twitch. I got one picked out. This person is working on Advent of Code in Python. So if you're interested in watching some more Python programming, stick along with the raid. We'll go to this person, and they are working on Advent of Code, which is like some coding challenges with Python. So looks pretty cool to me. That's going to do it for me for now. Thanks again for watching, everybody. I do hope everyone has a good day and a good weekend and all of that. I will catch you next time, whenever that one may be. Thanks. And then I think we awkwardly wait here because I think it does like a countdown. So here at some point within the next some number of seconds, it will rate us.